So, yeah, I will be talking about heterodyne detection in terms of ultra-high frequency gravitational waves. I found it inspiring to see that we already have two waves in our understanding. We have the electromagnetic radiation, which expands, who knows from where to where, but we have also a low frequency of electromagnetic radiation that still we need to understand. And we pretty much know everything about electromagnetic radiation from radio to gamma ray wave. And then on gravitational wave side, what we know, actually we know gravitational waves that have been detected from LIGO. So we are talking about frequencies of a few hundred of hertz, which corresponds somewhere in this electromagnetic wave spectrum. And also recent probably discovery of the pulsar timing search. Now, on the ultra-high frequency gravitational wave side, we want to access this region through looking electromagnetic wave. And the same question can apply for lower frequencies. Can we detect the lower frequencies in the same way? This is something that we don't know yet, probably in the future. So if we can place in the, like the LISA experiment, magnetometers that can measure the magnetic field very precisely and see oscillation over a range of days or months, probably that's an indication that a gravitational wave has changed a magnetic field background. That can be the magnetic field of the universe or something that we already know or we can measure. And on the other side now, here I will be talking about the higher part of the frequency region and try and see if there is some sensitivity for high frequency, like optical frequencies. And yeah, is needed a definition. Maybe we can redefine the terminology in the new white paper, because at the moment I found this useful definition in this book where it starts to display the definition for gravitational wave frequency, starting from very low frequency and low frequency, high frequency, very high frequency, and ultra high frequency. Are terms that usually are used in many things. If I talk to LISA team, they in their own band where they will have low frequency and high frequency. And if I talk to LIGO detectors, they will have low frequency and high frequency. So it's like a problematic, and we need probably to redefine. Maybe the best way is to use the electromagnetic wave, where we can talk about radio gravitational waves or microwave gravitational waves and so on, because that really catch the idea of the frequency. So we know both of them are waves, and probably we need to redefine the terminology about definition, what is a gravitational wave. Yeah. With that said, how we can look for optical gravitational wave? We are talking about frequencies that are infrared frequencies or optical frequencies. And this is a plot that I borrowed from, like shining from, like image, like shining from the wall, like outside experiment, which look for dark matter. And as you have seen, there is a synergy between searching for dark matter and the gravitational waves. Same way you can think, okay, I have a source, I don't know, I don't want to focus on the source now, but I want to estimate what's my sensitivity by looking photons that are emerging through a magnetic field. What happens is that the gravitational wave stretches space and time, and what happens to the field flux is stretching the field flux. And you will have always a coupling, and that the coupling depends directly on the amplitude of the wave, and the B field is very important. Longer is the interaction length and coherent, higher you will have the coupling. And if you try to put everything together with the action and the gravitational Lagrange and electromagnetic Lagrange, you can for sure compute a flux of converted electromagnetic radiation for a stochastic. Stochastic is easy, is present everywhere in every direction, so you don't need to answer a lot of technical questions. And of course, on the other side, you have a flux that you measure with your photodetector. Combining them together, okay, you can place some limits on that minimum magnitude that you can observe, which is proportional to the number of photons, the surface area, the section, the B field, length, the frequency range where you're looking, and the photodetector quantum efficiency. This has been done already from axion experiments like the one cast at CERN that was looking for axions converting in their magnetic field, like frequencies we are talking about, X-ray frequencies, and ALPS at DAISY that we were looking for converted axions, or OSCAR at CERN. All of these experiments, they share common things. They have a magnetic field and a detector in the dark to look for photons converted, depending on their frequency range. Same question you can ask about gravitational waves. And yes, it's possible. And here we studied their sensitivity to gravitational wave, and we assumed that they are seeing all the stochastic gravitational wave background. And for OSCAR and CAST, for example, they give the best limits. Was possible to put actual limits in this plot. Here you see the amplitude versus frequency in logarithmical scale. And it's nice to see in logarithmical because you don't get depressed there. Because the sources that you might think, okay, is this bond here, the BBN bond. And you think about sources at these high frequencies, okay, this can come from primordial black holes, have evaporated, have a lot of high frequency components depending on the mass. And our sun, our lovely sun, is emitting gravitons towards our detector, and they can convert. Then you think, okay, what's next? Where these we're heading up this this experiment like the ALPS do. They have longer magnetic field. They're going to have cavities. Well, what happens that they have higher sensitivity? If you want to calculate what's the sensitivity for ALPS2 in terms of gravitational wave. Yes, and also YAXO, which is a future experiment for future upgrade for that will upgrade CASTA, will have bigger surface area and higher field. That can also improve the detection or observation of high frequency, ultra high frequency gravitational waves. So what we have done here is to look for single events with conversion of the graviton in a Fabry-Perot cavity. So we have assumed that there is enough coherence time to build the field and so on. That's are all questions that will go towards what source is going to be found. But let's try to get the best out as in terms of sensitivity. With a transistor edge detector, you count single photons. So single photons that can convert it. And then you have your Fabry-Perot cavity will have this line shape where the sensitivity will get enhanced. So you have a finesse factor. They call it as like quality, how much resonates the finesse, or how much you can enhance the field inside the cavity. So if you get a production of gravitational wave due to a gravitational wave, optical gravitational wave, you get an enhancement. And you can probably count these photons in this frequency region at way high sensitivity. Then the next question is, what if I have another field inside, like already an electromagnetic wave, and I get a conversion? This is called the heterodyning. This is used for ALPS, for looking for the axion. And can we say something about gravitational waves? So if you have two fields that are inside the cavity and you compute what is the field square, or better, the intensity, you will have a term that is going to be gravitational wave term, that we already know the field which we are not interested in, but we're going to have an intensity that gets modulated with a frequency difference. And this is called the heterodyning technique, this term here. And if you are able to look at the frequency difference, you will have a field oscillation. The power of this is like you don't need a transistor edge detector, and you have the gravitational wave amplitude being linear instead of quadratic. So we are talking about fields amplitude that are very small, being quadratic, or even smaller. Yeah, but one can object, okay, you have a signal at frequency difference, but if you integrate this signal, it goes to zero. That's a problematic thing. But let me go a bit and break down how the heterodyning works, first of all. And imagine that we have these two beautiful sinusoidal signals happening in our cavity, one a smaller amplitude, the gravitational wave, and the other is the local oscillator. We call it local oscillator because it's the field that we know the amplitude, we know for certain. And we do the magnitude square, as we did before, and we have this term here. So if I see what I see in my signal is going to have an envelope that will be modulated like intensity modulation at the frequency difference. And here I'm plotting only the two, this small range. How can we recover this information? It's possible. So the way how to do it is you need to sample or to acquire the signal while it's oscillating. So you need high frequency data acquisition in order to see this frequency oscillated. And then you say, what frequencies do I need? I need frequencies that I'm interested in. So we need to sample very fast in order to see this oscillator in magnitude. Then, next question, okay, we have beautiful coherent signal, and we can probably demodulate. We call it demodulate, so we multiply by a cosine term, and we get out our signal. So it's possible to do. But we are talking about stochastic gravitational wave background, so how we can deal with the stochastic. So now we come to another issue, because stochastic has a random phase and a random frequency. That complicates stuff. Now, okay, very good. But stochastic has a nice property. It's coming somewhere from our universe, and the phase front of the stochastics is very huge. What if we have two detectors that are co-located in space? They will be able to see some part of the sky where the signal is correlated, like the CMB detector. If you do cross-correlation of two-point function, you see temperature fluctuation. And can we place two heterodyne detectors close to each other in order to see the same signal? My believing is yes, because this phase front of stochastic is very huge, and we will have intensity modulation of the field in similar way. So if we have two of them, probably we can recover a signal. Imagine that the gravitational wave will produce a noisy signal because it's stochastic, and what happens to our intensity signal will be fluctuating like the blue one here. And how is the way to recover that signal? We need to use a way how to detect the two signals having same property and see all of these fluctuations are identical. And this is done through the so-called cross-correlation. So we will have the two detectors that will see a fluctuation of the magnitude at same way, and we can cross-correlate. So the gravitational wave signal will have its own phase that will be similar, and we don't need to use demodulation in this case. So we don't need to synchronize our intensity to a source that we don't know or whatever. But if we have close them collocated, we can recover a stochastic background. That's OK, making this assumption. Now we want to understand what's the sensitivity that we can achieve. However, you are limited by noises. And the noises that are limited in a detector are shot noises. Shot noise, for example, if you go to frequencies above frequency difference, so we are talking about a frequency difference omega, or better, optical frequencies that are different, like on 1 megahertz or 1 gigahertz. This is the maximum that you can do. And you cross-correlate them, and you read out the signal-to-noise ratio is proportional to the number of photons that you detect in the integration time. So we know what the number of photons are because we have already calculated the flux, and we can place everything together and calculate now what is my amplitude with a signal-to-noise ratio of 1 with a cross-correlation, and given that we have a time integration. Then, yes, you get an amplitude which is actually minimal amplitude sensitivity, which is similar to the heterodyne. So you don't get much enhancement. But so if you compare the dark counts with the time integration, so dark counts usually for a test are pushed up to 10 to minus 6. And if you integrate for 1 million of seconds, you have similar value. Then the aperture will be the same, field will be the same. And then you just you can play a bit with the bandwidth if you can have higher or lower bandwidth with the heterodyne. The good thing of the heterodyne is recovering the complete signal because you're doing cross correlation. The test can have a signal, but you don't know if that's a spurious or real signal. So having with the heterodyne a cross-correlated lamp, you probably can say that something is coming because my magnetic field has been disturbed. All technical noises here are assumed to be uncorrelated. And it is possible. Cross-correlation has been used for various experiments. Now, I started a new position at AI, and we are focused on precision interferometry for fundamental interaction. And here I will present also the idea of the heterodyne by analyzing the polarization. So can gravitational wave couple to polarization? Yes, and this is one of our objectives. Other objectives that we have is vacuum magnetic birefringence and scalar pseudoscalar field dark matter. So we are I'm starting there a new position, so we are hiring also postdocs and PhD. So polarization of the light is another aspect that I would like to enhance and understand better. And the light has two main polarization, and we know that is S and P polarization. If we sum them together, we can get the linear polarization. What's the good thing that the polarimetry that we intend to build can probably can study rotation of the polarization if the magnitude of one of the component is oscillating with some frequency, because it rotates the field. If it is oscillating in phase, what if it's oscillating out of phase? Then we can have that our light becomes elliptical. So polarimetry study both of them, and and has been already validated and studied for vacuum magnetic birefringence, like the PVLAS experiment, where vacuum becomes birefringent and makes the polarized light elliptical. And this has the polarimetry technique has given the best result on measuring this tiny effect, but still unmeasured. So here you have the effort from 1990s to 2018 on measuring this tiny effect, but has not yet been measured because the QAD value is here and all the measurements are above that level. So what is the strategy here? So we inject the polarized light like the one here, and if something happens to what we call medium inside, will make the light becoming elliptical back to linear, elliptical, or better oscillating this ellipticity. And we monitor the intensity, and we beat that with an ellipticity modulator, and we get this heterodyne detection scheme. So we have two ellipticities that are beating together, and we can get very high sensitivity in polarization. Then when you look at the signal, what's my signal? So because we are interested, I'm going to have a noise spectrum. This is my heterodyne frequency, a signal. And we can tell something about the noise. And if there is a coherent signal, this can be, for example, gravitational wave noise, or it can be a signal due to coherent signal gravitational waves. Or what else? Or VMB. So VMB will show like a modulation of the ellipticity at twice the frequency of the field modulation. And this is our intention. So to do VMB also with using magnetic fields. But how can gravitational wave couple? Now think about a linear light with only magnetic field, okay? The VMB is static, and we don't care, so we don't modulate the field. And suppose that we get a gravitational wave converted into electromagnetic wave, and we have two possibilities of our polarized light: getting disturbed, and can be this distortion here can make the field a little bit elliptical or rotated if it is in phase or out of phase, or noisy. So this is some work in progress that we have started with Andreas and Francesco, and we have to work on. But it's possible that with the polarimetry we can for sure say something about any fields that have been converted into the magnetic region. Polarimetry can be used also for other things like studying the dark matter. And we have some dark matter models like the scalar one and pseudoscalar one, and how we can probably do experiments to probe this region of scalar field and pseudoscalar. If we place like a highly birefringent medium, that what it does really is just keep the polarization linear. If with a fixed range, the scalar field dark matter, if interacts with my birefringent medium, will expand, and that expansion will generate my light elliptical. And I can measure this ellipticity with just placing a crystal inside at high sensitivity, because it has been shown to be very high sensitivity. And also gravitational wave, like a resonant bar, can disturb my crystal. So you can use it for both searching scalar field and also scalar field dark matter and gravitational wave. Now, what about the axion axion search? The axion rotates the polarization. So we need a long interaction length, and the field, what does to the field? It rotates at some frequency. Where is the frequency of the axion? And we need to accumulate this rotation. What we just use, we use two quarter-wave plates to accumulate with back and forth or with a round trip. And in this way, the light still becomes elliptical at the frequency of the axion, and we can say something about the axion search as well. If we project the sensitivity, we have to take into account the polarimetry noise limitation, like relative intensity noise, seismic noise, and all other coupling that can happen into this simple setup. And estimating this, we can probe region of parameter space for the scalar field dark matter and the axion search in this way. So there will be also a work in progress for the gravitational wave search. But this is the message that I want to give. The heterodyne has a lot of possibility to search for high-frequency gravitational wave in the optical range. And with that said, just thank you for your attention.